Molecules are not flat, they exist in three dimensions. Understanding the three-dimensional arrangement of atoms is crucial in organic chemistry, as molecular shape directly influences physical properties, reactivity, and biological activity. Chemists use specific visual models to accurately represent these structures. Several common three-dimensional representations help us visualize molecules. The wedge-dash model shows bonds coming out of or going behind the plane. Newman projections are used to study conformations around carbon-carbon single bonds. Fisher projections are especially useful for carbohydrates and amino acids. Sawhorse and perspective formulas further clarify spatial arrangement and rotation. Stereochemistry examines how atoms are oriented in space. The difference between molecules such as enantiomers and diastereomers lies entirely in their three-dimensional configuration. These differences can dramatically alter chemical reactivity and biological activity. For example, one form of a drug may be therapeutic, while another could be inactive or even harmful. In organic reactions, understanding three-dimensional orientation helps predict mechanisms and product formation. Reactions like SN1 and SN2 substitutions, E1 and E2 eliminations, and addition reactions depend heavily on spatial factors. Molecular modeling software allows chemists and engineers to simulate and analyze these interactions. Three-dimensional structural representation bridges the gap between molecular theory and real-world chemical behavior. It enables engineers to visualize, predict, and design better chemical processes, making it an essential skill in chemical, biochemical, and pharmaceutical fields. Isomerism explains why compounds with the same molecular formula can have different structures and properties. Isomers are molecules with identical formulas but distinct arrangements of atoms. There are two main types: structural isomerism, where the connectivity of atoms differs, and stereoisomerism, where the spatial orientation of atoms varies. Both types are fundamental in organic chemistry. Structural isomerism, also called constitutional isomerism, occurs when compounds share a molecular formula but have different atomic connections. For example, C4H10 can be NN-butane, a straight chain, or isobutane, a branched chain. Other types include position isomerism, where functional groups shift positions, and functional isomerism, where different functional groups exist, such as ethanol and dimethyl ether. These isomers often have distinct physical and chemical properties. Stereoisomerism arises when compounds have the same connectivity, but differ in three-dimensional arrangement. Geometrical isomerism, like cis and trans forms in 2-butene, results from restricted rotation around double bonds. Optical isomerism involves chiral molecules, such as D and L-lactic acid, which are non-superimposable mirror images and rotate plane polarized light differently. Structural isomers differ in bonding sequence, while stereoisomers differ in spatial orientation. Both types impact chemical behavior, physical properties, and biological activity. Understanding isomerism is crucial for designing drugs, studying biomolecules, and creating materials with specific properties. In chemistry, arrangement matters as much as composition.
In chemistry, the way atoms are arranged in space is crucial for understanding how molecules act and interact. Let's break down three key concepts: configuration, symmetry, and chirality, each essential for chemistry and biology. Configuration is about the fixed three-dimensional arrangement of atoms around a central atom, which can only change if chemical bonds are broken. Take 2-butene as an example. It comes in two forms, cis and trans. Although both have the same formula, their different configurations give them distinct properties, making configuration a fundamental concept in molecular chemistry. Symmetry describes how evenly atoms are distributed in a molecule. If you can split a molecule into two identical halves with a mirror plane, or rotate it around an axis and it looks unchanged, it's symmetric. Benzene is a classic example, with its ring structure showing high symmetry. Chirality means handedness. A chiral molecule's mirror image cannot be superimposed on itself, just like your left and right hands. Lactic acid is chiral, and its two mirror forms can behave differently in biological systems. Configuration sets structure, symmetry brings balance, and chirality creates uniqueness. Together, they shape how molecules function in chemistry and life.
Stereoisomerism in organic chemistry describes molecules with the same molecular and structural formulas, but different three-dimensional arrangements of atoms. A key type is optical isomerism, which involves molecules that can rotate plane polarized light. These optically active compounds include enantiomers and diastereomers, both crucial for understanding molecular behavior. Enantiomers are pairs of molecules that are non-superimposable mirror images, like left and right hands. Each enantiomer contains at least one chiral carbon atom, bonded to 4 different groups. They share identical physical properties except for the direction they rotate plane polarized light. One is dextrorotatory, rotating light clockwise, while the other is levorotatory, rotating it counterclockwise. A racemic mixture, containing equal amounts of both, is optically inactive. Diastereomers are stereoisomers that are not mirror images and arise when molecules have 2 or more chiral centers. Unlike enantiomers, diastereomers have different physical and chemical properties. Meso compounds are a special type of diastereomer. They have multiple chiral centers but are optically inactive due to an internal plane of symmetry, as seen in mesotartaric acid. Optical isomerism is vital in pharmaceuticals, where one enantiomer can be therapeutic and another harmful. In biochemistry, only specific enantiomers are used by living organisms. Optical activity is measured using polarimetry, helping chemists determine compound purity and configuration. Understanding enantiomers, diastereomers, and optical activity is essential for chemistry and life science.
In 2 minutes, I'm mapping the fastest route through 8 core reaction types you'll see in organic chemistry. First stop, substitution. Picture a crowded carbon where one group tags out and another tags in, like swapping teammates mid-game. SN1 waits for a carbocation. SN2 is a single clean hit from the backside. Addition. Take a double bond, add across it. Hydrogenation puts H's on an alkene to make an alkane. Hydrohalogenation drops H and X on. The double bond becomes a comfy single. Elimination. Reverse the vibe. Kick out a leaving group and a hydrogen to build a double bond. E1 if a carbocation forms, E2 if it's one concerted move. More bonds to oxygen or fewer to hydrogen. Primary alcohol to aldehyde to acid. Secondary alcohol to ketone. Think adding oxygen weight. The comeback tour. Ketones to secondary alcohols, aldehydes to primary alcohols, using H2PD or NABH4 LAH as the electron donors. Make a ring. Intramolecular reactions pull 2 ends together. When geometry fits, rings form fast. 5-membered rings. 6-membered rings are the chill sweet spot. Tension relief. Epoxides pop open when nucleophiles attack. Under basic conditions, under acidic conditions, regiochemistry decides where it opens. Substitution and elimination race each other. Addition and elimination are toggles on alkenes. Oxidation and reduction are opposite lanes. Cyclization and ring opening are door close, door open moves. Now a quick, clean synthesis of a common medicine, aspirin. Start with salicylic acid. Do an acetylation, an acyl substitution, using an acetyl source to replace the phenolic hydrogen with an acetyl group. Boom! Acetyl salicylic acid. That's aspirin. Along the way you saw substitution as the hero move, plus concepts that guide side reactions and purification. Remember, mechanism arrows are your GPS. Track charges, follow the best leaving group, watch sterics. Thanks for learning with me. Last frame says, thank you.
Drug molecules play a crucial role in modern medicine, helping to treat, prevent, and manage a wide variety of health conditions. Understanding how these molecules are synthesized is essential for pharmaceutical development and innovation. Today, we will explore the synthesis of 2 commonly used drug molecules, paracetamol and aspirin. A drug molecule is a chemical compound that interacts with biological systems to produce a therapeutic effect. These molecules can be natural or synthetic and are carefully designed to target specific processes in the body, such as reducing pain, fighting infection, or lowering blood pressure. Some of the most widely used drug molecules include paracetamol, aspirin, ibuprofen, amoxicillin, and metformin. Each of these drugs has a unique structure and function, tailored to address particular medical needs. Paracetamol and aspirin are especially well known for their pain-relieving and anti-inflammatory properties. Paracetamol, also known as acetaminophen, is synthesized by reacting p-aminophenol with acetic anhydride. The process involves acetylation, where the acetyl group from acetic anhydride attaches to the amino group of p-aminophenol. forming paracetamol and acetic acid as a byproduct. Aspirin, or acetyl salicylic acid, is synthesized by reacting salicylic acid with acetic anhydride. In this reaction, the hydroxyl group of salicylic acid is acetylated, producing aspirin and acetic acid. This simple yet effective process has made aspirin one of the most widely used medications worldwide.
Thank you.